All right, good morning, everyone. Hopefully, all of you are doing all right in this extreme weather. It so happens that this is the second time we are seeing it during our semester. So, because of that, our exam is now going to be postponed. I'm going to provide the new date. It's most likely going to be 16th of March, so the week after you come back from your spring break. So, you'll have 1 week after you have come back. So I'll provide that information on the Canvas page, so you have information about that. Because of this change, there will be few other changes as well in the second half of our class. So I will change few things in the syllabus, and I'll also notify about the updated schedule for few things that we have after the second half. There were some guest speakers and all those things which I need to rearrange in some way. But I'll let you know within a day or two. So that would be sort of some changes that we will expect in the second half, including your exam one. Before I start, I'd like to take any questions you might have. I did not receive any questions regarding the exam preparation, so I was assuming that everybody is fine with whatever you are preparing. But since the exam has been postponed, I'm happy to take any question you might have before we start. All right, so I'm not seeing any questions. What we're going to do today in this virtual session, is we will go over classification and regression trees. We will also go over discriminant analysis and ensembles, as well as the uplift modeling. Now, these are important approaches, techniques that are widely used in companies. So we will learn how we apply them, what exactly are these tools. As always, the Python models associated with these different techniques are going to be provided as a video. So you can take a look at what we have in our notes readings and how it was run. So you get to see that in those videos, and you can replicate it so that you have an understanding of how to actually model them. You'll have assignment regarding these topics. So I will be posting the assignments after the class. There will be case analysis, as well as an assignment which requires you to do Python programming and run these models. So that way you get to experience how exactly these models work. So first we will start with classification and regression trees. These are quite reliable. These are very transparent. In other words, we actually know what's going on in this model. Unlike, let's say, neural network, where we will see later that it's quite difficult to explain to anybody what exactly happened. We only know what the results are in the end. But here we can show step by step exactly what is going on. So these are also called decision trees. Essentially, these are flexible methods that we can use both for classification and prediction. Right? So this is something which we will be using to split the data into smaller and smaller groups. So if we have, let's say, a data of 5,000 customers and we want to put them into different groups, we split them into groups based on some predictor variable that will be of importance. And essentially what we're trying to do is create each group as pure as possible. In other words, we don't want to mix, for example, premium customers and basic customers. We want to have a group of customers identified who are clearly premium, and a group of customers identified who are clearly basic. So that's something which requires some metric for purity that we will talk about. How do we decide whether it's pure enough? So think of it like sorting M&Ms by color, but with some data, right? Now, the beauty of this technique is that the rules are very simple, that we can really explain it to any non-technical boss also. And they actually can understand what we are telling, right? Unlike some of the other techniques which could be black box. So we'll take a look at how this actually works. Let's take an example of the streaming services, which is what we have now been accustomed to, the Netflix of the world. So we will understand based on watch time of a customer, based on the devices that they use, based on the engagement with the streaming service, how likely they are that they will be a subscriber. And there we can have, for example, how long the watch time is and how much the engagement is in terms of the number of months or number of years that they have been with this particular streaming service. So here we could say something like, if someone watches more than 3 hours per day and uses multiple devices, then they are probably addicted enough or engaged enough to pay for premium, right? So we see that there's an if-then statement which we use. So there's an if and then there's a then sort of a statement that we will use. So in the end, it looks like a tree like this, where there's a root node where all the customers are, and we are asking a question, for example, do these customers watch the programs for approximately 3 hours per week or greater than 3 hours per week? So they can be a true or false depending on which direction they go. If they go true, then we take a decision, which is the next step. So if they have watched for 3 hours, then the second question would be something which relates to how engaged they are with it. Do they keep switching their channels or something like that? There could be another decision variable for which again they can be a true and false. So we keep doing this until we reach the terminal node, which we call the leaves, right? So those are what we see here. So that's something which we are doing here. The decision nodes are up there and terminal nodes down here. And typically you'll have in binary trees, the number of terminal nodes will always be exactly one more than the number of decision nodes. Right? So for example, there are 4 terminal nodes and there are 3 decision nodes. So that will be true for binary scenarios. So that's sort of the mathematical reality. So how do we actually use a tree to make predictions? It's relatively simple. You take a new record, let's say a new customer, and you drop them down the tree. Now, for example, we saw the tree in the last slide. At each decision node, we are asking, does this customer meet the condition, whatever condition it is, number of hours that they are watching, or how many times they watch a certain serial, or whatever the case might be. And then it could also be, for example, the income. Let's say if their income is greater than $99,500, for example, then they go right. If it's less than, then they go left. You keep doing this at every decision node until they hit bottom. When they finally land in the terminal node, that's your prediction. In classification, we are looking at all the training data that ended up in that node and take a vote. We'll see that later, that when we eventually reach that terminal node, we look at how many out of, let's say, we started with 5,000 customers, and by the time we reach the terminal node, one of the terminal node, let's say, have 180 customers in it based on all those if-then statements. Out of the 180, we see how many of them are actually premium customers and how many of them are basic. So for instance, if out of 180, 100 of them happen to be premium and 80 happen to be basic, majority is premium. So we give that entire terminal node a classification of premium. So basically it's a majority vote kind of an environment. So this is basically going through this process and for each terminal node eventually giving a certain classification. So we keep doing this in most of the cases. Now it's a recursive partitioning system. Basically, the word recursive just means we do the same thing over and over again. We keep going from the top decision node to the next decision node. Every decision node, we determine which variable might be the best variable to reduce impurity, because that's what we want to do. And this could be, for example, we start with annual income. Eventually, it could be something else. Once again, annual income can come back. So these initial predictive variables can come back at a later decision node, which is something which we see many times in decision tree. So for each split, we calculate how much it would reduce impurity. Basically, how much purer could each groups be. Then we pick the best split, the one that makes our groups most homogeneous. That's the goal here. we want the group to be as homogeneous as possible. Then we take each resulting group and do it all over again. So that's the recursive part of it. We keep doing this. And we keep going until we can't improve things anymore, or until we hit some stopping rule. Right? There is a stopping rule that we can specify, that if the impurity is less than, let's say, some value, only then do it. Otherwise, stop, or just do it for 5 times and then stop after 5 times. So we could give some stopping rules, which helps in reducing the level of complexity that this tree can take. In fact, it's also useful not just for complexity, but also to reduce overfitting, because oftentimes these trees also have one of the negative feature, which is they overfit the training set. So that's something which we will take also a look at later. Now in the readings, obviously there's a lot of details which you will have to go over, but I will explain some of these through this presentation. We have 2 different sets of data which we will be using. One is a very simple data, not too many data points here. It's the gym membership data. We have seen this before. There are 24 members, 12 of them premium, 12 of them basic. Right? So we have equally split them. For each member, we know 2 things: how much they spend monthly at the gym, maybe on smoothies or personal training or any of those protein bars or whatever else, and how many hours per week they work out. These are the 2 variables we have. And the gym wants to predict who is likely to upgrade to premium membership. Why? So they can target them with special offers. Right? It's like they are reading your mind, except it's just good old data science that we are trying to do here. Now, looking at the data, we can already see some patterns emerging. So if we see these orange circles and blue diamonds, we see that there is some sort of a split between the 2 already by just looking at a scatter plot. But what we want to do is do better than just a visual check of this, and actually predict what way we can distribute them into different groups. Right? So that's something which we will take a look at, how we can determine this. Now, in reality, when we are running these decision trees, what it's trying to do is it's creating rectangles. It's splitting this scatter plot into different rectangles that can create more purer subgroups. So for instance, if I were to run the decision tree, the first split might happen at, let's say, monthly spending of less than, this is in thousands of dollars, so $60,500. Now that is the first sort of vertical line that we see here, and we can see that on the left hand side we have majority of them as blue diamonds, and there's only 1 orange circle. On the right hand side, it's still sort of a mix of the 2, but more orange circles. So we are already seeing that this line was created with an understanding of purity metric and where should that line be, so that it can reduce the purity metric, the overall impurity. Right. So in the left hand side we have 7 basic and 1 premium, so that's about 87.5% basic. On the right hand side we have more number of premium members, 11 premium and 5 basics, still mixed, but leaning towards premium. Now the split has reduced our impurity significantly, because if you see, before we split this, in the data we had 12 premium and 12 basic, which means 50-50, and that's the highest level of impurity that can be there, right? Because you're equally split. But after the split, we got 1 rectangle that's almost all basic, and the other that's mostly premium. So we are making progress this way. The algorithm basically chooses spending over workout hours as our first step. We chose monthly spending rather than workout hours as our first variable, because this variable created the purest split, and sometimes that's important to recognize what's the most critical variable. Now, I mentioned impurity a few times. How do we measure it? We have few metrics. One of the common metric that classification trees and regression trees use is the Gini impurity index. There's a formula that we are using here. Essentially, this Gini index is 1 minus the sum of squared proportions. Right? So 1 minus pk is the proportion of case in a rectangle A that belong to class K. So if you saw the previous one, we had two different rectangles. For each rectangle, we had a proportion of premium and a proportion of basic. So we can basically find what exactly the proportion of basic was and proportion of premium was for each rectangle. And then we are going through this calculation, which results in providing us the Gini impurity index. The maximum happens to be when there is 50% proportion, right? So that's 0.5. That's what we have here. And when we go either left or right, we are reducing the impurity, and that's something which is what we are trying to do here. So in our gym example, if you take the 50% split of 12 premium and 12 basic, the way this Gini index would calculate is 1 minus 0.5 squared minus 0.5 squared, right? So because there are two different proportions of 50% each. So 1 minus 0.5 squared minus 0.5 squared will give us 0.5. The final value will be 0.5, which is the maximum level of confusion. And on our first split, the left node would have a Gini index of 0.219 if we were to just use the right proportions of the basic and premium that we have on the left. It'll be 0.219, which is less than 0.5, which is much better. And on the right node, we would have a Gini of 0.430, still better than 0.5. So we are making progress. That's what the tree keeps looking at. The other metric that it also uses is the entropy measure. We could use this as an alternative measure. And the formula again is minus the sum of pk, which is the probability of a certain class k being in a certain rectangle A, times log to the base of 2 of pk. Now it's a complex formula, but I think the formulas are not the important part here, but there is some sort of mathematical background for calculating these impurity. And essentially what we just did for Gini index, we could, if we were to use entropy, we could simply substitute the same values that we talked about the proportions of premium and basic members, and determine what exactly the total entropy will be. So that gym example, in this case, 1 will be the maximum disorder, and after the first split, it actually drops down to 0.779 by simply using that formula that we have here. So we are trying to see how far can we go in reducing these entropy and Gini index measures of impurity. Now the tree doesn't stop at just one split. We just saw one split in our previous slide. What we are doing is recursive partitioning, which means we're recursively trying to improve things. After the first split, we look at our new two groups and ask, can we do better? And the answer is usually yes. So we split again. For the gym example, the algorithm decides to split the left group again. And this time it splits at monthly spending of $51,000. I'll show you in the next slide. So essentially, if I go here, you can see that this was our first split at $60,500. The next split also happens on the monthly spending variable only. So now what we can see is the left of this $51,000 is all of one class, basic. The middle has one premium and rest of them are basic, and then the right one remains the same that we had started with. So the left one is now having a Gini index which is perfect. It's a homogeneous group. So that's something which we have done as a second step. Now we keep doing this, as we'll see, and you can see that also in the readings as well as the Python model that I will also put the video of, that if we keep doing it at stage 5, we keep splitting it for 5 times. So this was our first split, this was the second split, and we keep doing this, there will be these many rectangles that will be formed, and we can see that majority of them are pure and homogeneous sets. So this is all blue diamonds, these are all orange ovals, orange ovals here, blue diamonds here, and this one also has all the blue diamonds. The only one which has two different ones are one of the blue diamond and one orange oval. So this is the small rectangle in the middle that you see, which is not yet homogeneous. So this would be something which we would do, and we had only one time when we used the weekly workout hours as one of our variable for split. So every time it's basically doing the same thing. If, for example, the monthly spending was less than whatever dollars, in this case the amount it was. So actually it was not annual income, it's a monthly spending. So it's $60, $61, whatever that is. And then we keep doing that if then statement, and eventually there was one time when we also use the weekly workout hours. If they have spent a certain number of hours weekly, that also determines whether they're going to be premium or basic. So it's continuous recursive if then statement which results in an outcome. But now this one was a very simple data set with only 24 cases, just for illustration. In reality, we would have a more complex data set, right? For example, in the reading, we will have a different data set, which is ShopSmart, a fictional but realistic e-commerce company, which is trying to grow its Prime subscription base. So we have got data on 5,000 customers in this case who were offered a premium subscription in a campaign, right? We sent a campaign saying that join us for premium. Out of these 5,000, only 480 of them actually subscribed, which is 9.6%. So this is what we call an imbalanced data set. We've got way more no than yes, right? Way more of basic members than premium members. So what now we are going to do is we'll use some predictors. So ShopSmart has 12 predictors for each customer. For example, demographics could be the age of the customer, income, education, their shopping behavior could be their monthly orders, for example, how long the account age is, and engagement metrics like whether they are mobile app users or not, did they save their payment method in the system, etc. So that's a lot of information. And the goal is to build a model that identifies which customer are most likely to subscribe, why, so that we can target them more effectively in the next campaign, because that's the goal. Otherwise, we'll be wasting marketing dollars on someone who orders once a year, and we would rather focus on power shoppers who are already halfway to subscription. So this is where decision tree really shine. We can actually handle multiple predictors and find the patterns that matter most. So we'll take a look at how the decision tree looks like for this data set. Again, same recursive approach, but we will see a very simple, for simplified view of a full tree. Full tree is much larger, but this is what it would do. First, it will start with annual income of certain amount, and then starts with a certain training set, which we have chosen 60% of the data we'll use as training set. And then what it's doing is it's splitting into true or false. Is the annual income less than or equal to $99,500? It's true. Then we go here. Then we check whether monthly orders were less than or equal to 3.55 on average. And then the next step, and so we keep going down until we reach the terminal node. So we can see that every time there is a split of those who are basic and those who are premium members. Right, so based on which one is larger, the color of these rectangles are also indicative of whether this particular node belongs to a basic member or a premium member, depending on the majority. So majority here is basic, here also basic, here also basic. So this goes all the way down by keeping on going with true and false until we reach the terminal node here, when there's no more impurity reduction that can happen. There's at this point we also have this false, which is monthly orders less than or equal to 3.55, which means false would take us this way, which means they have monthly orders greater than 3.55. Then we look at another variable here, whether the education level, which is indicated there after post high school, maybe how many years they've studied or whatever that might be. And that's something which also is then helping us determine the terminal nodes. So we have reached this point, and then we again have true and false, and depending on how the split happens, where the majority is, we give that particular node either a premium or a basic categorization. And eventually there is also this credit card limit for the customer, which is used for true and false. So this is a simplified one. When we'll see a full tree, you can take a look at that in the reading also. It will be very complex. If we don't stop it from growing, it can grow very large, and in the end, many of these we will not be able to actually even see what that if-then statement was. But the challenge is that if we also run it for a full tree, which is let the tree keep growing recursively, there is an overfitting problem. It will do very well with the training data. In fact, it will be perfectly matching the training data. You'll have an accuracy of 100% because it will learn everything about the training data by keeping on doing the recursive partitioning. But then when you try doing the same thing for a validation data, it will not do a great job. In fact, it'll start increasing in its error. So this curve starts to go up as we go further up in terms of the number of splits of the tree. The tree complexity keeps on growing. After a certain point in time, it also starts to grow higher in terms of the error rate. We don't want that. We actually want the results to be as good in the validation set as it was in the training set. So there is always a sweet spot of the number of splits that we should have that balances complexity with generalization. And as part of data mining and machine learning, we also want to know what that right split should be. And that is something which cannot be done simply by randomly choosing some splits. We have to have a systematic approach that allows us to actually identify what that sweet spot might be, what's the right split that can help us get the best result. So that's something which we will understand how we can do this as the next step. Here what we typically use is cross-validation. So single split is not good because that is misleading. A full tree is also not good because they are unstable. They also are overfitting the training. So we need to know what is the right split. So we do this by doing something called cross-validation, by creating multiple folds of cross-validation. Essentially, we are creating multiple versions of the data. 5-fold CV would mean that we are running this model 5 times in different versions of that data, different random samples of that data being taken out, and we understand what exactly is the accuracy level, what's the range of the accuracy that we have in those 5 different versions of the model that we ran of data that we ran. So for example, in the readings, you'll see that it's from 96.2% to 98.2%. It gives us some confidence that, okay, this particular model is doing great, at least it's in this range. So that's something which we try doing here, which is looking at multiple versions of the data and see different tree structures that will be formed, because every time you use a different version of the data, different random selection of cases from the data, the tree structure can be quite different from each other. But if in the end the accuracy is turning out to be somewhat similar, then that is something which is a good indication of whether our tree structure is doing a good job or not. So we would try to prevent overfitting by doing certain things. One, we could also reduce the number of times that the tree is going to split. We could say only go for maximum depth of 3, 4, 5 instead of going all the way till 71 different splits and making it a very complex tree. We can specify some of these parameters. So maximum depth is basically saying stop splitting after X levels. It's like telling your tree that only become this much tall, after that stop splitting. So 3 to 10 is typically what works very well. Whereas if you see the readings, you'll see the full tree goes quite further than that, and that will be way too much. The second thing could be the minimum sample split. So for instance, we can require that a node that has been created by this tree split should have at least X number of records before we allow it to split again. So if you have already split few times and the node only has 50 sample in it, we can say that at that point you should not split anymore. So we could specify minimum samples to be there in a node for it to be split again. Third could be minimum impurity decrease that we require. We only make a split if it improves purity by at least X amount, right? So no more tiny improvements on noise. We want some major improvement on noise. So for instance, we can say if a split only reduces impurity by 0.0001, it's probably not worth it. We can choose that number, whatever that impurity, minimum impurity decrease we want. Now the challenge is finding the right values of these parameters, right? These again cannot be arbitrarily chosen. We want to be systematic about it, what the right value of these parameters should be, because too strict a rule that we choose here and our tree will be too simple. It'll underfit the data, and if we make it too loose, and that would result in a very, very large tree, it'll be an overfitting. So there's a challenge of finding just the right number that we want to set up here. So once again, just like the cross validation that we talked about earlier, there's an approach that we can use to determine what might be some right values for this, which we call the grid search solution. What we do here is that we try different parameter combinations and we let Python do the job, right? We don't have to do this permutations and combinations. We define the range of our parameters. Maybe we tried maximum depth from 2 to 16. We could try minimum sample split from 10 to 100 and minimum impurity decrease from 0.0001 to 0.005, right? So we are choosing certain ranges. And then the grid search, what it does is it tries every combination of these. So it'll be several permutations and combinations. So which basically means, for example, if we have 14 values for depth, like 2 to 16, we have 14 different values for depth that we want the tree to go. And 12 for minimum samples, let's say, we have chosen 12 different possibilities of minimum samples, and 3 for impurity. So then it will be total number of combinations will be 14 times 12 times 3, which is equal to 504 combinations, which is a large number of combinations that the grid search will build these many trees, 504 different trees in the backend, and test each one using cross validation that we just saw in the previous slide. Cross validation is using different samples and running that model with these combinations. And the winning combination is the one with the best cross-validation performance. So in the reading, you'll find that when we run this kind of approach of grid search with cross-validation, we find that the maximum depth of 5 actually works very well. Minimum sample split turned out to be 10, and minimum impurity decrease turned out to be 0.001. So that combination was helping us get the best result. So that is what we could do and have a more systematic approach for determining what is the way we set the parameters and how the tree should grow. Now there's a downside to this. This can take a long time, 504 trees times 5-fold cross-validation, because we have these 504 trees that are being run 5 times each with cross-validation. This is 2,520 trees to build and evaluate. Now the computer can take a long time to do this. I mean, nowadays with fast computers, we can actually achieve this very fast. So that's something which we have to keep in mind. Now, if we have many more parameters to tune, then we have a technique which we call randomized search CV. Instead of actually specifying the exact number of values for depth and minimum samples and impurity, we can use something called randomized search CV. It randomly samples combinations rather than typing them all. So instead of doing all possible combinations, it randomly selects different values and then does the same thing that we just talked about. It just takes lesser time by doing that. It has to be truly random though. So that's also something which we can do and has been explained in the Python program that you will see in the reading as well as in the video. Now here's what that tree which has 5, the depth of 5 looks like, is something which we can see in this case, where we have multiple variables that are being used for identifying our splits at different points. The grid search had find 5 as optimal. Any deeper we go, we will be overfitting. Any shallower, and we might be missing some important patterns. We only used 5 predictors out of the 12 possible predictors, and the tree did automatic variable selection for us. So that's what we see every time it's doing the variable selection, the predictor choice and variables that we will be looking at as important ones. So this way we are ensuring that our tree is not very large. At the same time, it is accounting for all these different factors that we wanted to take into consideration, like the minimum impurity, etc. And this tree ends up getting quite a good amount of accuracy, like we are reaching 98.8% accuracy on both training and validation data set. And the gap between the training and validation data set is also very small. So we have eliminated most of the overfitting as compared to what happened earlier when we ran the entire tree. So this way we are not memorizing anymore, but we are learning as part of this tree. So the rules are also quite interpretable. Like we can just show this to the manager and they can understand exactly what's going on and on what basis this entire growth of a tree. So we can just choose this particular link that goes from annual income less than or equal to $99,500. Then we check whether they had a monthly orders of less than or equal to 3.55, yes or no, and then keep going down, and then we determine that they were basic. But on the other hand, we can also see which ones will be premium based on other characteristics. So that's what we call pruning of trees, and this is the result of a well pruned tree, which has less complexity, more information, and also interpretable. So all this basically indicates that trees can be quite valuable for decision making, data mining. They are transparent. You can actually see and explain how trees are made. We cannot do the same thing with neural networks because there are a lot of things that are happening in the black box. Second, these are automatic in terms of variable selection. The tree only uses variables that actually matter. So in our case, we ignored several predictors. We only used the ones which were important in our shopping example there, e-commerce company. So that's useful because then we don't have to worry about all these different variables that will have to be considered. The third is they are robust to outliers. The trees don't care about absolute values, only the ordering, which variable is more important and what are the values within that. So if you had, for example, a billionaire customer in this data set with income really large, it won't throw off your tree like it would in a linear regression, because linear regression can become sort of wobbly if we have such disparity. The tree just says high income is equal to right branch and it moves on. So they just go in the right branch and it keeps doing that. Finally, we also have fourth, we have this transformation issues that we typically see in parametric methods like linear regression. We sometimes have to transform the variable using log transformation or something like that. Here we don't need any transformation. We don't need to normalize. We don't need to standardize the variable. The tree doesn't care if one variable is in dollars and another is in years. It treats all variables the same. So this way there's less pre-processing, less work for you, more time for actually doing some analysis here. And all of these make trees excellent off-the-shelf classifiers. They work well with minimal tuning, which is always great to have, right? So we can have mixed data types and we can do all this. But we have to keep some limitations in mind too. First, it's unstable. We have talked about this earlier, that small changes in training data, depending on what was the training data, if you chose 60% of the data as the training data, small changes in that training data can lead to completely different trees. That's why we did cross-validation using different subsamples. So that's something which we have to keep in mind. Second, they are data hungry. Trees need reasonably large data sets to work well. If we only had 50 records, for example, a tree probably isn't our best choice. The third would be they miss diagonal patterns. You notice that when we were doing this split and I showed you the rectangles, they were all very vertical or horizontal splits. We could not see any diagonal lines. So it's always rectangle formation. It does one variable at a time, making rectangular regions. But if the real pattern in the data is more diagonal, which happens many times, like linear regression, when we have seen that there could be a line which is not going vertically or horizontally, it might be going in a certain angle, then trees can struggle. So that's something which we have to be aware of. And then fourth, variable bias, basically predictors with many categories or predictors which have many unique values have more potential split points. So they are going to be more likely to appear in the tree. Right? If, for example, annual income, there are several different values that we see in the data set. That particular variable will keep coming back as a decision variable. So that's something which we have to also keep in mind, that there is that variable bias that can happen in this case. That's the last one, the high cardinality predictors. There's a favoring of that. Now, this discussion that we had about decision tree was about classification, whether into basic or premium, using a tree structure. Now, the same tree can be helpful also when we want to predict some continuous variable, like what exactly is the price of a certain product. We could do exactly the same thing, but we call them regression trees now. The difference is that instead of predicting categories like subscriber, non-subscriber, prime versus basic, we now are predicting numbers. It's like predicting the price of a used car, a house, how many hours you're spending on Netflix this week, etc. So number two, terminal node predictions are different in this case. In classification, we saw that we took a vote, majority vote. If we had two classes, we saw where majority were, and we gave that node a classification of that specific subcategory. But in regression, what we do is we average all the values that might be there in that node. So for instance, we keep running the tree and we reached a node where, for example, our objective is to predict TV prices, the price of a TV. And in one of these nodes, there are 10 TVs after having gone through several splits. And we want to know what's the price for that node, because we cannot just say it's low or high. It's not a categorization or classification. What we will do is we will take the price of all those 10 TVs that are in that node and take an average. So that's what regression tree does. It basically averages. Then the third one is impurity measurement changes. Instead of Gini or entropy, which we used in classification, we now use sum of squared errors, which is what we have seen earlier also. Sum of squared errors is also used for regression, which we did earlier. So that way we are trying to understand if the sum of squared errors is low or high. If it keeps reducing, we keep doing it. Everything else exactly the same. We still split recursively, still need to avoid overfitting, still need to tune the parameters like we did. So that's something which is consistent across classification trees and regression trees. All right, so that's sort of our discussion on classification trees, regression trees. Now, random forests is basically a committee of trees, right? So what happens if we have lots of trees? Because single trees are unstable, we saw that earlier. So a solution could be that we build lots of trees, and random forest is that particular technique when we build many trees on random samples, right? So random sample works like this. It randomly samples your data with replacement. It's called bootstrapping. The word bootstrapping basically means that we are taking out some sample from the data. So if we had 5,000 customers, we randomly sample some numbers from there. Then we replace all of these back into the data set. The next time we'll take out another sample of, let's say, 3,000, run the tree, then put these 3,000 back. So every time there's a chance of some of these 3,000 coming back in your sample, some of them not coming back. Now for each sample, we build a tree using only a random subset of predictors at each split. Right, so we are again choosing, even the predictors are going to be randomly chosen for each split. And then we'll repeat this hundreds of times, thousands of times. Again, this can all be automated in Python. And for each new record, we'll drop it down all the trees and take a vote. In the end, what exactly it eventually is telling us for classification. Or regression, we would take average prediction like we did with regression trees. So it's like asking 500 people for directions instead of just one person. And that way we are more likely to be right in what we are doing. So that's what random forest does. It's an extension of classification trees and regression trees, but running lots of trees with randomly chosen samples and a randomly chosen subset of predictors. The good thing about random forests is that along with doing the classification and regression, like we saw, it also tells us which variables are more important. So this is an additional benefit that it provides. It gives you the variables that are really more important for the tree formation or the forest to determine which one getting better accuracy. So in our e-commerce example, the annual income of the customer is the most important in predicting premium membership subscription. So that's it's showing it there. It provides slightly better accuracy also. We'll see, you can see in the readings as well as in the Python model that is there, that by using random forest we have slightly better accuracy than single tree. Not very big improvement, but small improvement, but still something which is important when companies are looking at investing money on certain things. And then the random sampling and random predictor selection adds variety to the forest. Each tree is quite different because it saw different data first of all, and then it also used different predictors. So this kind of diversity is actually good because it means that the tree makes different mistakes, and when you average them out, when you average all these mistakes across multiple trees, these mistakes are going to cancel each other. So there's the advantage of random forest. But the downside is that you cannot visualize a forest like you were able to do for a single tree. A tree can be visualized all the way with if-then statements, but the random forest, because there are so many randomly created trees, we cannot visualize them. So you lose the interpretability advantage here, but accuracy typically goes up. So that's random forest extension of classification trees and regression trees. There is another extension of classification trees and regression trees which is different from random forest. These are called boosted trees. Now notice that random forest, what it was doing was it was parallelly building multiple trees by using different random samples and random predictors. Boosted trees does a slightly different thing. What we do here is more of a sequential process. It's like having a study group where each person focuses on the question the previous person got wrong. Right? So we are focusing on things that were not correctly predicted. The process will be build a tree, then find all the misclassified records. Wherever the records were misclassified, we can always look at that from the results. Then build another tree, but this time what we'll do is we will oversample the mistakes. Anything which was incorrectly predicted, we will have more of them in our sample that we are going to use, and give them higher probability of being in the sample, and then keep repeating this many times. Every time we are choosing more of the records which were misclassified in our sample, and then we combine all trees with weighted voting. Later trees get more weight than the earlier trees. So this is something which we do. Instead of building independent trees like random forests, we build trees that explicitly learn from each other's mistakes. Tree 1 might have struggled with high income non-subscribers because there were a lot of mistakes over there. Tree 2 may says that okay, I'll take care of this, and focuses on those cases. So that's something which can be done. In our e-commerce example that we just talked about, boosted trees were especially good at finding that rare class of subscribers because they kept focusing on misclassified subscribers from previous rounds. This is also something which is widely used in many of these machine learning competitions. It's powerful because it does focus on mistakes, but it can also overfit if you're not careful. Also, like random forest, we cannot visualize the process easily in this case as well. So both of these techniques, random forests and boosting trees, they trade interpretability for accuracy. They have better accuracy, but the interpretability is not as good as trees. So that's something which always need to be kept in mind. Here are the key takeaways from what we have discussed. First, that decision trees work by recursively splitting data based on predictor variables, basically simple if-then rules. Number 2, trees can overfit quite easily if you let them grow too large. Right? So we want to use some techniques like limiting the depth, the minimum samples that we should have, cross-validation, grid search, all those things to find the sweet spot. Third, trees are awesome for interpretability. You can show them to non-technical stakeholders and they will understand exactly what's going on. Single trees can be unstable. That's something which we also want to be aware of, that they can be unstable if we have only one tree. So random forests and boosted trees can overcome this limitation. And then fifth is use trees when you want good performance out of the box with minimal pre-processing. We don't need to pre-process, we don't have to normalize the data, all those things are not required. They handle mixed variable types, they handle outliers well, they also handle missing data quite well. So that's where I think we have talked about the regression trees, the decision trees, classification trees, and extensions like random forest and boosted trees. We also talked about how exactly we can prune those trees and ensure that we are considering a limited number of splits and all those things. So here I'll pause and see if you have any questions that I can answer. Okay, I'm not seeing any questions here. So I'm going to move on to the discussion on discriminant analysis, which is basically an extension. All these three techniques that we're talking about are extensions to each other in many ways. So discriminant analysis, we'll see a very strong connection with what we just talked about with decision trees. Here we are going to actually use a statistical method. Now, decision tree was not using any parametric technique. There was no major, except for the mathematical formulas for impurity calculation. There was no statistical background there. We were not worried about any of the distributional assumptions or anything like that. But discriminant analysis will be one where we are interested in statistics and methods that rely on statistical techniques. So what is this technique? Imagine that you're at a party and there's this really perceptive bouncer who can tell just by looking at you whether you are a VIP or not, right? So they can basically discriminate in some way which kind of a customer you are by looking at your characteristics and figuring it out which club you belong to. So this technique does exactly the same thing. It discriminates data and determines which group it belongs to by looking at something called distance, and we'll see later what that distance means. So it classifies records into predefined groups, uses distance using something called class means, what exactly the class looks like on average, and does this data look very similar to that, and it also accounts for correlations between between classes as well as between characteristics of individuals. So that's what we are going to learn a little bit about here. It's very widely used technique, not widely seen in machine learning classes, but it's a highly used technique, an important one. It's used by banks to decide if you're creditworthy. Doctors use it for diagnosis, which is way more serious than sorting some gym members that we talked about earlier. Forensic scientists use it to classify ancient skulls. There is also authorships, disputed authorships are many times resolved using discriminant analysis because that helps us determine sort of the patterns in writing for different authors. It has also been used to classify everything from bonds to customer types for decades. That's why it is an important technique, and we need to understand how it works and how it builds over and above what decision trees can do. Or there obviously will be limitations for this technique also, but where this could be valuable. So we go back to the same gym membership example, and at least understand how this technique will be differently applying something to the same data set as compared to the trees that we talked about. So in the gym membership example, our challenge was, can we predict which gym members will upgrade to premium based on their spending and workout habits, right? So these were the predictors, and the goal was just to determine which way we can separate them. Now we saw in the trees that we were doing this vertical and horizontal rectangle formations, and we were trying to make them as uniform or as homogeneous as possible, each of these rectangles. Now if we put the same scatter plot again and take a look at that scatter plot with a slightly different lens, which is discriminant analysis type of lens, what we can see is that instead of a vertical line, if we had the ability to use a slanting line like this, then we could have done better than sometimes just using a vertical line. So this example, we can see that there are only three of these premium and rest of them are all basic, and here there are only two of these basic, rest of them are all premium. So this actually already has done a better job than what our first split was in the previous example with trees. So here we can think of this, so we have to somehow determine how this line can be created, right? That's the goal of discriminant analysis. It does something similar to regression models, where in regression models also we are trying to determine a line that can predict our overall data set very well. Here we are trying to create a line using statistics which can differentiate between different classes. So we can think of a linear classification rule as a line that separates these two-dimensional space into two parts, with most of these premium members in one half plane and most of the basic members in the complementary half plane, the other side. And the good classification rule would separate the data so that the fewest points are misclassified. That's something which we can do. Now, in this case, we just did it by hand. I'm not using any discriminant analysis model, but I just wanted to sort of use a different way of splitting and see that by just doing this way, we were able to do better than some of the tree structure that we found earlier. But can we do better than this is the question that discriminant analysis answers. Now here's the core idea. The whole idea boils down to one single question: which group is this particular case closer to? Right. So this is something basically imagining that we are in a party and we would typically gravitate towards people that we are closest to, and that's the same concept here. We measure how far your data point is from each class average. We call that a centroid in this case. Like when we have different classes, basic versus premium members, there is a class average for each of these two different categories, and that's called the centroid of that class. And then we can determine for a new customer which centroid value does this customer's characteristics come closer to, and then that would be the class or category in which this customer will go. The key insight is that distance matters, and here we will try to calculate that mathematical distance, which will help us determine which class this particular customer should go to. Now, we have seen the idea of distance earlier also in one of our previous discussion when we talked about Euclidean distance in k-mean approach, k-neural networks, KNN techniques and all those things. So here we are using a slightly different distance calculation. So Euclidean distance has some problems, which is why this discriminant analysis would not use it. The problems are that it's unit dependent, dollars versus thousands, whatever the unit that we are using will then make the distance calculation flawed. If dollars were calculated in thousands of dollars versus tens of thousands of dollars, then that would actually make a big difference. Different answers we will start getting. Similarly, the second problem is that it also ignores the variability in the data, how much the spread in the data is. That can become challenging if there's a lot of standard deviation in the data, because average is not everything. So sometimes variability is also an important one. The third thing it also ignores is correlation between the data sets. And sometimes that correlation matters for us. And that is something which we want to explicitly account for. These variables can be correlated with each other, and we need to ensure that we have accounted for that correlation. So that's where this alternative approach called the Mahalanobis distance or statistical distance comes into play, which has the benefit that it's unit free because it's standardized and it does not worry about which unit we are using. It fixes all three problems. It does not care about the units. It takes into account the variance issue. It also handles correlations, right? So that's something which is what discriminant analysis uses. And the way we calculate mathematically is sort of a little cumbersome, but just to show those who want to learn a little bit on the back end what exactly happens in this Mahalanobis distance, it's essentially using sort of a transposed matrix calculation here. So we are using this symbol basically captures the variable. Each case is looked from the centroid of the class, and the distance between the two are calculated, and then we are transposing that matrix and then multiplying it. So it's a matrix multiplication which allows us to calculate this. But this kind of math will not be something which we'll ever be testing, but those who are sort of intrigued about this method is different from the way we calculate Euclidean distance, which is simply for each data point we are comparing as compared to average where it belongs and squaring and then summing them, taking a square root. That's what we do in Euclidean distance. But in Mahalanobis distance, we are doing something different. So that's essentially taking care of correlations, also taking care of the standard deviation among the data points and the variables within variables, and also it accounts for different units. Now, using this idea of distance, statistical distance or Mahalanobis distance, what discriminant analysis does is it creates a function, just like a regression creates a sort of a equation, which we call a regression function. Here we create a Fisher's linear classification function, which looks very much like a regression equation. We are trying to find a linear function that maximizes the ratio of between class variability divided by within class variability, because we want more of these within class people being together, similar type of people being together, in our case of e-commerce, for example, or gym membership. So that's what we'll do. We will maximize between class differences but minimize within class difference. This way we are trying to ensure that we are creating more homogeneous group. It's efficient, it's elegant, and it has stood the test of time. That's something which we have seen in many examples that it has been useful. The method basically creates a classification scores for each group, and then highest score will win. That's what we do, and something which we'll take a look at a little later in this slide as well, slide presentation later. So that's the way the process works here. Essentially, we calculate the class centroids where the mean of each class is. So premium membership versus basic membership of a gym, where the class centroid is. Now the class centroid can be a multi-dimensional, because many times we are using several variables to determine where the centroid should be. So it can be a p-dimensional variable. So as against just using two variables, sometimes it can become more in a hyperplane. We can then compute the covariance matrix. Again, it all happens in as part of the model itself. It computes the covariance matrix after having calculated class centroid. Then it generates this classification function that I was mentioning earlier, the linear classification function, Fisher's linear classification function, more like a regression equation. And then what it does, it scores each record for all classes. So every single customer, for example, is given a score, a value for both of the classes. Let's say in this case, premium and basic, we had two classes. It will give a score of what is the score it gets for the premium class and what is the score this customer gets for the basic class, and you assign the class which has a higher score between the two to this customer. So if the customer got higher score for the basic, the customer becomes a basic customer. If the customer got a higher score for premium, the customer is a premium customer. So that's sort of the approach, the technique that we use here. And along with score, there is also another thing which we do in this technique, which is moving from scores to probabilities. So those classification scores that already helps us identify which class should this customer belong to can also be converted to probabilities. There's a formula that we use, essentially e to the power the score that we have received divided by sum of e to the power of all scores that exist. And I'll show you again in one of the subsequent slides how this works. But this way we are transitioning towards probability. Instead of just saying you are in class A, we can say you are 78% likely to be in class A and 22% likely to be in class B. And that's sometimes more helpful for companies to have that kind of understanding. So we are converting those classification scores into actual probabilities using this exponential formula that software takes care of. But that probability can help you rank things, right? It can help you target the top 100 most likely premium members for a marketing campaign. If we know that we want anybody who has more than 60% chance of being likely premium member, we want to target them. This probability can be more beneficial than just knowing the score. It can also help with adjusting some cutoff threshold. We can decide, is it 80% or 60%? We can decide that threshold here. So that's the benefit of having these probabilities as against scores, which is similar to like what we did in lift curves and ranking for that. Right, so this was our by hand versus sort of using discriminant model. We could actually get a better distribution also. That's something which this slide is trying to highlight, that class separation. Essentially what it does is it creates a line, the linear classification function line, which then is based on that distance idea and the idea of the scores that we're giving based on this classification function. Now there are some assumptions that this entire technique has as its backend, because it's a statistical technique, it's a parametric technique, so it will have some statistical assumptions. One, that predictors should follow a normal distribution. It works well when predictors are normally distributed, but oftentimes in businesses many variables don't follow that, and what has been observed is that it's surprisingly robust even if that assumption is not met. Right, so it is not a very strict assumption, but it actually does very well if the variables have normal distribution. Number two, the correlation structure should be similar across classes. That's an assumption that it has, that the way your variable relate to each other shouldn't be wildly different between groups. So premium and basic members of, let's say, a gym, the way the annual income and monthly, the number of hours that they come for workout, the way they relate to each other in these two groups will be similar in these two groups of categories that we have created. That's an assumption that we have. It may not be true sometimes, that there could be difference in the way these variables relate to each other in the groups, but the good news is that that it is still going to be sufficiently well performing even if that assumption is not strictly met. It's close enough. Even if the correlation is slightly off, it works fine. So that's sort of something which is worth knowing, that there are some assumptions that we keep in mind when we are using it. If very wild violations exist, then we have to be careful about the interpretability of our model and ensure that we have realized this. The one thing which can really mess things up are the outliers. Those outliers can create results that can be wildly different from what should be there. So we need to remove these outliers before running these models. So that's something which is one of the care that we have to take when we run this model. Right. So that's the reality of these models, which we need to be accounting for when we are using it. Now, how do we evaluate the performance of discriminant models? We could create confusion matrix and determine how the accuracy levels are, the precision, recall, all those metrics that we have been using, we could use here also. We can also do the lift charts, ranking effectiveness, to understand how exactly the deciles are distributed and how we should be targeting these customers. And always these performance metrics have to be calculated on a validation data set and not the training data set. So that's something which we have seen earlier also, that we always test it on validation set and we evaluate our model on the validation set, because that's what the whole purpose of data mining and machine learning is. So that's sort of the idea of discriminant analysis, what exactly it does, how it works, how we evaluate performance. Now, there are some advanced features also that we have to keep in mind when we are using these models. the idea of prior probability. Now we took the example of gym membership that we just talked about, and we saw that we only took 24 members for making it simple, and there were 12 basic and 12 premium members in our data set in that sample. Now in reality, for that gym, it's possible that there were only 15% premium members in the gym, and the remaining 85% are basic members. But in our sample, the distribution was different, 50-50. So we want to sometimes adjust for this unequal class sizes in real population versus in the sample. And for that, we'll have to do something called a prior probability calculation, which is something which we can do as part of discriminant analysis. The second thing we also can do is misclassification costs. And we talked about this earlier, that in some practical applications, misclassifying one class is more expensive than other, like fraudsters. If you misclassify them, it costs you a lot of money, and you want to be careful about that. So in some cases, the mistake costs more than others, and that is something which we also can account for, integrate that into the classification function. So that's, as an example, I'll show you how it works for each of these, how we adjust for unequal classes and what exactly happens when misclassification costs happen. So going back to the gym membership example, where we had in the sample that we used 50% premium and 50% basic, but let's assume that in the real population there were only 15% premium members. Then to account for the distortion, we will have to do something with the classification function that we got. Now remember that I mentioned that the classification function looks like a regression function, and regression function, if you recall, there's a constant plus a coefficient, right? So a coefficient multiplied by variables that we are using. So constant plus some variable multiplied by a coefficient. So it's the constant that we have, which is also happening in the classification function. There will be a constant and some coefficients. That constant needs to be changed to account for this difference between the sample versus the population. So suppose we got the constant of minus 21.38 when we used this data of 50% premium gym members using the training set. Now, because we know that in the actual population we have way more basic members, we will actually have to add the log of 1 minus 0.15, which is log of 0.85, to that constant, and this new constant is what we will then use for calculations or for actually creating those discriminant function and creating the line with that discriminant function. So essentially it changes that line a little bit by adding this log value because of that difference here. So it's a small change that we'll have to make based on the prior probability understanding in a given data set in the real population. And when there's unequal misclassification cost, which was a second possibility, in that case we account for it by adding log of the two costs, log of cost 1 and log of cost 2 to the constant. Again, the constant is the focus here. So we are adding logs of the two costs to the constant. And the different way to do this could be that we just look at one of the two classes, class 2 for example, and simply add the log of the cost of class 2 divided by cost of class 1, and that will also do the job. So often absolute values are difficult to know. We will know that in misclassification in class 2 is 10 times more expensive. Sometimes that is more of information that the company has rather than absolute costs. Then in that case we can just take the log of 10 times, so log 10 and something like that, which can then help us do this. And we saw this kind of calculation also earlier when we talked about misclassifications and doing something like this for taking care of that misclassification when we talked about other methods as well. So it's same technique, same approach that we will have to account for. Now discriminant analysis, we talked about it for two classes, basic versus premium in the gym membership case, but it can also be extended beyond two classes, right? For example, customer churn risk data, if we have that, and we are trying to categorize low risk versus medium risk versus high risk customers. We now have three different classes, and therefore we will have three different classification functions, one per risk level. When we had two classes, we would have two different classification functions. So it's just having three different classification functions, and each customer is scored for each of these three categories. And exactly like what we did for binary two class scenario, we assign the category with highest score, right? So we'll see this as an example, and this will also explain what I was mentioning about the two class situation. So let's take this example of customer churn risk. Essentially the same procedure that we were talking about, but we are looking at three classes: low risk, medium risk, and high risk of customer churn. And we have several variables, whether it's peak usage, a recent complaint that the customer had, active subscriber or not, are they premium tier, etc. So all these variables are there, and we know for every customer what exactly these are. Some of them are binary values, and some of them are monthly spend is a continuous variable. And we know currently what their churn risks are for each customer. For every line, we know what the current risk is. Now, if we run this with discriminant analysis, and there is a Python model that I have shown in the reading and also shown in the video, you get an output like this, right? Once you run that model, you get an output where, like the regression function, you'll have coefficient and intercept, right? So we have a constant, which I was mentioning earlier, which we need to be fixing if there is misclassification costs different or prior probability is different. So there is a constant which is given here. The first row is constants for the three classes: high risk, low risk, and medium risk. And then we have all the coefficients for different variables that are being used. So minus 0.98 times peak usage, plus 15.31 times recent complaint, and so on and so forth. So exactly like a regression equation, but this is three different classification function with a constant and all the coefficients. We also get to know the confusion matrix precision, not very great values, but that's what we have based on running this model for three classes here. And we can then also show that confusion matrix here, right? So this equation is what now we will take into account and understand what exactly we will do with these constants in case there is there's a prior probability difference between the classes. So each of them have an equation, and all these once added together. So when we take that constant minus 0.98 multiplied by peak usage for customer 1. So if I go back and show you this, I can look at the first customer, peak usage was 1. So that minus 0.98 will get multiplied by 1 plus 15.31 multiplied by whatever the recent complaint was. It was a 0, so it will get multiplied by 0, and we keep doing that for the first customer, and we get a value for the first customer for high risk. Similarly, for the same first customer, we'll use this set of values and get a value for low risk, and the third value we'll get for the same customer will be the medium risk. For each customer, we will get three values of classification function, and we will decide which class that customer belongs to depending on which of these three values is the largest, right? So if it happens that the low risk value was the largest, we will classify that customer as low risk, which is what you see in the next slide. So the first customer is classified as low risk. Actually, it was a low risk too, because you can see that in our actual data, it is a low risk customer. But in the discriminant analysis also, we classify it as low risk because these are the values we got for the scores. The score for high risk, when we just substituted those values with the intercept and all the coefficients for high risk, was minus 15.05. For low risk, it was minus 0.66. And for medium risk, it was minus 0.76. So out of these three values, the largest value is minus 0.66. Remember that in negative numbers, a smaller negative number is a larger number than a larger negative number. So minus 0.66 is the largest of the three. Therefore, we are categorizing that first customer as low risk, right? So that's what we are doing. Now we can as we were talking earlier about this, that scores can be converted into probability, and that is using the exponential formula that I had shown earlier. So this is how it works. For instance, if I want to know what is the probability of this customer being medium risk, I'll take the score of medium risk, which is minus 0.76, exponentiate it, e to the power minus 0.76, and divide it by e to the power the three scores, e to the power minus 15.05 plus e to the power minus 0.66 plus e to the power minus 0.76. So this ratio is what is giving us 0.47, right? So that's what we were talking about earlier. So it's a technique which allows you to get the scores, determine which class it belongs to based on which is the highest score, and it also allows you to capture some of this propensity or probability of being in a particular class. So high risk has the highest probability, also 0.53. Now, why do we use discriminant analysis? First off, it's fast. It is computationally very fast as compared to some of the modern deep learning methods. Second, it is a small sample wizard, while other methods may not do a great job because you only had very small data points. Discriminant analysis can take care of even smaller data sets and do a good job with that, right? Doesn't need too much data to learn. It's typically shown to be, research has shown that it's actually 30% more efficient than logistic regression. That was another technique that we learned earlier for classification. So this one is a better technique based on research than logistic regression in many cases. And then feature importance, it also tells us that which features actually matter, which sometimes is super useful when we are understanding the data and explaining results to the boss, right, to the executives in the company. So in that way, discriminant analysis can have some benefits. It can be useful for small to medium data set with well separated class and can do all these things that we just talked about. So key takeaways for discriminant analysis is that it classifies based on statistical distance. Mahalanobis distance is the other name for it. We use Fisher's linear classification function to calculate these values and then determine which class the customer or whatever the case is belong to. It handles multiple classes naturally. It's efficient with small data set and it's robust to assumption violations. So that's something which is what this method does. All right, now again pausing to see if you have any questions or clarifications about discriminant analysis or decision tree that we talked about earlier. All right, not seeing any questions at this point. So what I'm going to do is move on to the discussion on our ensembles and uplift modeling. Right, so ensembles and uplift modeling basically is assembling a super team with different models and averaging all the values that we can get from all these different models that we ran, and then that would be our final result, right? So it's basically something which got popularized after the $1 million Netflix prize, which happened in 2006, where the competing teams that were competing for this prize actually realized while competition that if they combine their models, they actually can do far better. So this is where it started. So the story was that in 2006, Netflix was doing DVD rentals. Now they don't do this. They don't have that business component anymore. They wanted to improve their movie recommendation system to every customer. So what they did was they released a sort of massive pile of anonymous movie rating data to the public, and they asked public to use this data and beat their current system that they have of determining whether this customer will actually subscribe to their system or not, and if any of these models can beat their current system by 10% or more, then they get $1 million. So many data scientists actually started to compete for this. They competed on a public leaderboard. There was a public leaderboard which kept informing how well each team is doing. And here's where it gets interesting. Some teams started noticing something fascinating. That is, when they combined predictions from multiple models, which different teams were using, the results were becoming more accurate than a single model can do. And quickly, it was also possible to do this averaging of two prediction sets, then to build one perfect model, right? You can always get two different models, run them, average the outcome, and that would actually be faster than trying to find what is the best perfect model for us. So even if one model would have done worse than the other, combining them usually improved the results. So what this resulted is the team started joining forces with each other, and the winning team was literally called Belcour's Pragmatic Chaos. That was the winning team here. It was a super group which was formed from Belcour and Big Chaos teams plus some extras. So these were the two major teams, but other teams were also joining, and they won the $1 million by combining hundreds of different models into one mega ensemble. Ensemble basically means combination of models. So this contest proved that ensemble methods weren't just theoretical, they worked spectacularly in practice. And that's where the ensemble revolution started happening in machine learning. Now, why do they work very well? It's because of this characteristics of error cancellation. Basically, imagine you have two models. Model A tends to overpredict, for example. It's optimistic, always seeing the glass is half full, but model B tends to underpredict. It's pessimistic. When we average these two predictions, the optimism and pessimism basically cancel out, and we get something more accurate than either model alone would have done. Right? So that's the idea here. Same thing with averaging values also, like averaging arrival times. We can have quantitative values also. Now, the technical term for this is reducing variance in prediction error. Right? So we are reducing the variance in the prediction error term. So single models errors will bounce all over the place, sometimes way too high, sometimes way too low. And ensembles error are more stable because the wild swings in different directions tend to cancel each other out from the different models. So that's what it does. And the key point is that different models may make different types of mistakes. Right? So because if all the models were making the same mistake, then combining them would not help. But if they're making different types of mistakes, if they failed for different reasons, then averaging might actually work. This is why diversity in our ensemble matters. Different algorithms, different data samples, different parameter settings. We do these differences. We consciously put those differences and create those variety so that the error cancellation is happening and it makes the ensembles more powerful. Now, this is another interesting story that is basically capturing this, that simple averaging can sometimes be very powerful just by just adding and dividing the total would be something which ensembles can do. And this goes back to 1800s. Francis Galton was a statistician. He went to a county fair in England where they were having a contest, and the challenge was to guess the weight of an ox. Now people submitted hundreds of guesses and they were all over the place. Some people clearly had no idea what an ox weighed, and others were relatively close to what exactly the weight might be. But here's the kicker that actually blew Galton's mind, which is when he calculated the average of all the estimates, it was shockingly accurate, within actually 1% of the ox's actual weight. So the question was, how is this possible? And the answer is because all those wild guesses somehow evened each other out. The two high guesses balance the two low guesses. So that's what happens. The errors cancelled each other like perfectly balanced chaos, and this is the wisdom of crowd. That's what it's also referred to as commonly in this particular example. Some individuals were able to beat the averages, but in general, when you average them all together, you actually do better than otherwise. It's the same idea that some people win the office March Madness pool every year, but most people get crushed by the average. If you were to just average everybody's predictions, you actually are going to be more accurate. So same principle is applying in machine learning model also. So we'll understand this, how it works and how it can be adapted in the case of different types of prediction that we have to do in business. So this simple average approach is just averaging, nothing fancy. Just model one predicts is using linear regression. We are using linear regression here, and we predict $125, let's say, for something, or 125 as our outcome for that particular variable that we are interested in predicting. For the second model, we used a different model called regression tree. We talked about that, and that predicts 118. The third model we used was KNN, and that predicts 132. So we got three different predictions from three different models, which obviously have different parameters and all that. And when we do ensemble prediction, the simplest would be just to take the simple average of the three, and that will be 125, and that could actually be very close to what exactly the actual result might be. Right. So this is something which we can do. Now, sometimes we might want to take weighted average, which is give more influence to better performing models. That's something which can happen, not just simple average, but we can do weighted averaging. Or we can take the median instead of mean to reduce impact of one model going completely rogue, because sometimes extreme predictions, outliers can make means an incorrect way of doing things. So we use median instead of mean. Now, the beautiful part of this is that this works for both cross-sectional prediction as well as time series forecasting. We can use this ensemble method for types of different types of prediction challenges we might face in businesses. We have already talked about time series forecasting earlier. We have seen cross-sectional predictions in our regression discussion, as well as regression trees and all those things. So we can use it in both kinds of scenarios. So we'll see stock market forecasters have been combining predictions from different models for a very long time, partly because it works, partly because if the ensemble is wrong, they can blame the average rather than any single model. So this approach is simple. That's the core idea here. Now, there are different ways in which we can do this averaging beyond or create this ensemble final result beyond just averaging, and these are some other techniques that we can use. One is called bagging. Bagging is essentially short form for bootstrap aggregating. Right? Bootstrap we just talked about earlier, that essentially taking multiple samples from a given multiple subsamples from a given sample, and then run the model with that subsample, put that subsample back into the sample, and then again randomly select another subsample and keep running it. So, and then take an average of all of that. Right? So in this case, it's aggregating, bootstrap aggregating. So instead of using different algorithms on the same data, what it does is it uses the same algorithm on different data samples. So we could use the same regression tree on different data samples. The way it works is, step one, we generate multiple random samples from the training data using bootstrap sampling, which I've just mentioned, that it's simply sampling with replacement. You randomly pick records, and each pick goes back into the pool. So you might pick the same record multiple times in one sample. Right? This creates samples that are similar but not identical. It's like shuffling a deck of cards differently each time. The second step would be to train your algorithm on each sample separately, producing multiple models. Now, then we combine their predictions by averaging, which is what we just learned earlier, that it can be very powerful. And the reason why it works is because it reduces overfitting. Remember, overfitting is when your model memorizes the training data instead of learning patterns. So in this case, by training on different samples, we get models that each overfit slightly differently. And when you average them, the overfitting cancels out and the real patterns become reinforced. Now, bagging is especially useful for algorithms that are prone to overfitting, like decision trees and neural networks. These are very prone to overfitting. We saw decision trees just now. So these algorithms can get too enthusiastic about fitting training data, and bagging would rain on them. And random forest, for example, we just learned about that. It's one of the most popular machine learning algorithm. It's nothing but basically a bagged decision tree with extra randomness thrown in. So random forest is an example of a bagged decision tree. All right, so that's what bagging is. The other kind of approach of ensemble that is widely used is boosting. We talked about boosted trees a little while ago, and this boosting will sort of remind you something of what we talked about earlier. It's the idea of learning from your mistakes method. So instead of treating all data equally, boosting, what it does is it pays extra attention to the records where your model screws up. It's like uh, basically trying to give more importance to those places where we made mistakes and give less importance to where we were all right in terms of prediction. So the process will be to fit a model to your data, then identify which records we got wrong, which is misclassifications where we had large prediction errors. Third, and this would be the clever part, which is draw a new sample where misclassified records have higher probability of being selected. So we now are consciously creating a sample where we put more of the misclassified records in that sample, have higher probability of being selected. And now fourth step is fit another model to this new sample. Now we are running another model with this new sample, and finally fifth is repeat this multiple times until performance improves. We keep doing this every time we are oversampling mistakes, running another model, and keep doing this until performance improves. What you end up with is a sequence of models, now each focused on fixing the mistake of the previous models. The final ensemble will combine all these models weighted by their individual performance, and that's something which can be very powerful. So boosting is powerful and forms the basis for some of the best performing algorithms in machine learning, like XGBoost, LightGBM, CatBoost. There are many of these models that exist which you can easily use in Python. They already are functions for that. Now these are the algorithms that have been winning many Kaggle competitions also. Many real world applications also are using boosting technique, because it directly targets model weaknesses and fixes them iteratively. It's systematically improving on the mistakes rather than averaging them out. So that's the advantage here. Now, some important things to keep in mind about ensembles is that they are not magic bullets. There are advantages, but there are also disadvantages. The advantages are more precise predictions, reduced error variance. It helps in avoiding overfitting. We talked about that. It works with any algorithm, and it has been used in many contests and has done well there. Now, the disadvantage would be that it also has this resource intensiveness as one of the challenges. Resource demands are quite a bit. Computational horsepower, software, all these are in high demand when you're using ensembles. It requires analyst time because of all these different things to be run on that particular data set. Because you're building multiple models instead of one, which means multiple jobs, and you're trying to test each of these and averaging them or doing boosting or bagging. Now, boosting and bagging are somewhat automated, but they still have computational costs associated with them. The third thing could be ensemble requires multiple data sources and multiple models, right? So we need multiple data sources that needs to be collected. Sometimes that's not fun. And then it can be a black box. We don't know exactly what happened, because unlike tree where we can explain everything very neatly, here we are averaging or we are doing some bagging and boosting. The relationship between predictors and outcomes become opaque in this case. So it's not easy to explain. And finally, it can still overfit sometimes if we are not careful. Because if you obsessively tweak weights until you've memorized the validation set, then it basically is essentially overfitting given the data set that we have provided. So the bottom line is that we use ensembles when accuracy matters most, and we can afford that computational cost that it demands. And we skip them when we need interpretability, which is what we get in decision trees, or when we need speed, then we skip these. So that's sort of the drawback, positives and negatives of ensembles. All right, again, pausing before we talk a little bit about uplift modeling after this. Any questions here? Okay, not hearing any questions. The topic that we now discuss would be uplift modeling. Now, uplift modeling is something which is widely used, and we'll see this relates closely to one of the techniques we talked about earlier, but has some significant differences than that particular technique. So it's used in marketing quite a bit. Essentially, traditionally, response modeling that companies used to use in marketing was who will respond to our campaign, marketing campaign, right? We just want to know who will be the people who will respond to our campaigns. And that sounded reasonable, but the question leads to sending expensive promotions to people who were already going to buy, right? So what would happen is we'll send to all these people who we think, according to the model, will respond to our campaign, but some of these people would have anyway gone ahead with, let's say, subscribing to premium membership. We wouldn't have to send any of these expensive promotions to them. And that is sometimes very important to recognize, because there's a cost attached to this. Margins can be saved if you can avoid sending to those who would have anyway upgraded without promotion. So we want to be very precise in sending these promotions. So the right question is not who will respond to our campaign, but the right question is who will respond because of our campaign. And that's the question that we are asking in uplift modeling. That difference is subtle but critical. We are looking for what we call persuadables. These are people who are on the fence but who need a nudge, right? Those are the kinds of people we are interested in. Not the people who would buy anywhere because you're going to waste money, and not the people who would never buy no matter what, because there also you will be wasting money if you were to send them any promotion. Now, there's also a third group of people who are going to be negative uplift, those who get annoyed if you send any marketing to them, and they're going to be less likely to buy because you contacted them. They would have bought otherwise, but because you sent them a campaign, they would be now less likely to buy. You want to avoid them as well, right? So this is something which uplift modeling identifies, and it identifies these groups so that you can make strategic market to strategic people, send campaigns to positive uplift customers, and leave alone those who would have bought anyway, and those who would get annoyed. So this is basically using this A/B testing as its foundation, right? A/B testing is the foundation of uplift modeling. It's basically something which we use very much in science projects, in basic sciences. So it's essentially a science fair experiment for marketing in many ways. And the setup is relatively simple. You randomly split your customer list in half. Group A will get the treatment, in this case a promotional email encouraging subscription upgrades, and group B will get nothing, right? That's the control group. They are the control group. They're blissfully unaware of any of these experiments. And the reason we need this control group is because other things might be happening, and maybe there's a holiday season and people would have naturally upgraded more. Maybe a competitor is just raising prices which would make them to come to us. The control group lets us measure what would have happened without your campaign, if these people would have anyway joined because of other reasons. So in our example, group A, the one we are sending email, had 40.2% upgrade rate, right? That's what we got with these 5,000 customers. And group B, where we did not send any email, had 34.4% upgrade rate, right? So there was an upgrade in both cases, but there was a difference that one group got email, the other did not get the email. And the difference is 5.8%, and that's our campaign lift. Right? The lift from this email campaign was about 40.2 minus 34.4, about 5.8%. That's the average effect across everyone, which is not bad, because the critical part is random allocation. You can't let people self-select into these groups or choose who gets what. You cannot choose who will get promotional email and who would not. It has to be randomly selected, because that way we will ensure that any difference that has happened here would be attributable to just the campaign, not anything else. So that's the idea here. It's exactly what scientists do in science experiments, and that way we get the right result. So random as assignment is non-negotiable. We have to ensure that this is randomly assigned. Now here's why overall campaign lift of 5.8% would not necessarily tell the whole story, and we need to dig a little bit further into this. Our customers can fall into 4 different groups. We talked about this earlier. First are the sure things. These customers would have upgraded anyway, and we don't want to waste money on them, right? There's no point in sending to them because that would be wasted money. Second are persuadables. These are the ones who need a nudge. These are the ones we want to target because these are the ones who without campaign would not come to us. They are on the fence, undecided, and a good campaign can push them over the edge to upgrade. So the marketing ROI will come from this group. The third one are lost causes. They are not going to upgrade whatever you do, right? So no amount of marketing will change their minds. Maybe they cannot afford it, maybe they don't need it, whatever the reason might be, and marketing to them is throwing money away. And the final ones are these are the sneaky ones actually. These are the negative reactors. These people actually get less likely to upgrade when you market to them. So they find promotional emails annoying, and over contacting them will make them churn easily, right? So that's something which will make them unsubscribe from everything type of annoyed. So the overall 5.8% lift averages across all of these 4 groups, which is not what we want. What if we can identify which group each customer belongs to and market accordingly? Then send campaigns only to persuadables, leaving the sure things, the lost causes, and definitely avoid these last ones, negative reactors, right? That's what uplift modeling enables. More of a surgical precision instead of the spray and pray marketing that otherwise would have happened. So that's what we will do next. So how do we build an uplift model? It involves 6 steps that are pretty clever once we understand them. Step 1 is basically run your A/B test. Split your sample randomly, send the campaign to half, nothing to the other half, and record who upgraded. So we would record all those who have upgraded based on this. This gives us the experimental data needed, right? That's the first step. The second step is to recombine all the data. The treatment and control come back together. Now we split into training and validation sets and build a predictive model. Now in this, the key is to include campaign email as a predictor variable. Within the prediction model, we will have a predictor variable, which is the campaign email, alongside all the other features of the customer. The annual income, whatever other features we want about the customer, we'll include them, but we'll also include this one additional predictor variable about campaign email, which will be 1 or 0. Either we had sent a campaign email to the customer or we did not. So we are upgrading the outcome, which is whether the customer upgraded to premium or not, as a function of all the customer characteristics and whether they received the campaign. We are using both. Step 3 would be to score the model using each customer's actual treatment value. Basically, what we are doing is probability of success condition on the treatments. So that's what we have here. Probability of success conditioned on the treatment. And that basically says what is the probability of this particular customer going for premium membership given that we sent them a campaign email. So that's so this will be for the treatment group, right? And for the control group, it will be probability of success for with conditioned on no treatment for the control group, because we did not send any email to them, but they did sign up for premium. So what was the probability of success with no email? So that's an important step here. We do this probability of success with treatment and no treatment, and we do this 4th step, which is actually a rescoring. This is the real magic trick that we do here, which is reverse the treatment variable values. So wherever we had sent this particular email campaign, we will make them 0, and those we did not, we will make them 1. So we reverse that and rescore the probabilities again. So treatment groups now scored as if they got nothing, and control group scored as if they got the campaign. So we are reversing it. This gives you the counterfactual probabilities. We call that counterfactual probability. What if it was the opposite? What if it were counter the factual that we did? So in a parallel universe, what would happen? Now step 5 is we calculate uplift for each customer as the difference of probability of treatment minus probability of no treatment. Right? What happens if that same customer received treatment versus the customer did not get treatment? If we take the difference of the two, what happens? If we get a positive uplift, that means the campaign helps. If we get a negative value, then it means the campaign hurts. So that's what we do as the 5th step. And the 6th step is for future campaigns with new customers, just score them twice, once with treatment 1 and then with treatment 0, and calculate the difference. And we would know the uplift values. Positive values are the ones we want to target. Negatives are the ones we want to avoid. Higher positive value, more likely we should be targeting them, because the likelihood of them signing up will be more. They are the pursuitables. So here is an example that we have also discussed in the readings. So the top customers, for example, in this case 9464 is the customer ID, 2617, these are customer IDs. For each customer we had calculated the probability of the customer signing up for the subscription. With campaign for this customer was 0.87, without campaign it was 0.21. The difference is 0.66, an uplift of positive value. For the second customer, uplift of 0.65. So these are very good uplift values, and these are the customers we should be targeting. Right? So there's high likelihood that they will switch to subscription once the campaign is sent to them. But this last one is actually having a negative uplift and is the customer we should be avoiding in this case. So that's something which we want to not send a campaign to. So this is the kind of things we can do with uplift modeling, essentially being able to distinguish which customers, specific customers we should send campaigns to and which one should not be sent campaigns to. Again, this entire thing has been done with Python model, and there is that model in the readings as well as a video which will be posted that shows you how that model works. So that's the beauty of uplift modeling, and this is something which we cannot do with what we earlier did by just classifying them as someone who we want to send the email or not. That is not enough as an answer for this. Now the two main purposes of uplift modeling is contact or don't contact. Should we send this customer any marketing at all or leave them blissfully alone? Because marketers hate the idea that sometimes the best marketing is no marketing, but sometimes it's important that we should not be marketing to some people. It can not only waste money, but sometimes it can also make some people move away from the company by being annoyed, right? So we want to leave them alone. The second purpose is which message to send, which is when you're definitely running a campaign, which specific message should each customer receive? Should we offer 20% off or free shipping, or appeal to their fear of missing out? So we could also decide the types of campaign. Right now, the example that we saw earlier was an email or no email, but we can also do this in a more complex setting where we can decide the type of campaign that we want to send, and we can still do AB classification, AB type of testing, and analyze this using that technique like we just did here. And we can see uplift for each customer based on each of these different messages, and those who had the positive uplift will be sent the specific message that we have decided works for them. Right, so that's the uplift technique, which can also be used for different treatment options, and we can assign customers to whichever treatment gives them the highest uplift. And that's important. So two different purposes, and both of them are used in practice. So this is the final slide. Key takeaways: Ensemble combine multiple models for better accuracy, because in team, when you do this and average, it's actually better than individual models. Simple averaging often works because errors cancel out. Bagging is one technique which uses different data samples So it's a bootstrapped aggregating, which is what bagging is all about. And boosting learns from mistakes. It focuses on hard cases and then builds on that. Ensembles cost more but win more contests. So there's computational cost, but there's a accuracy advantage that we get. And finally, when we move to uplift modeling, this is the model which helps in finding persuadables, not just responders. And we do A/B testing, which provides an experimental foundation for this. And random allocation is critical in that process. We target positive uplift customers and avoid negative uplift customers. So that's the idea behind ensembles and uplift modeling. So with that, I think I have discussed what I wanted to discuss today, because it was a virtual session. I don't think we need the entire time, because there was not much of a discussion, not many questions either. But we have covered different topics for which you will have case study that you will be basically submitting your executive brief, and I'm giving you until the end of this week, the weekend, when you will submit that. These are related to the topics we covered, so it will give you some perspective on how it's applied and what exactly it means when we apply these. There's also an assignment which will require you to use Python program to run these models, and for that you'll get more time, so you will be able to spend some time on this. But other than that, nothing else I need to discuss at this point. I hope that your team project is working out and you're working with your team members as you move forward. You have a project presentation that's coming up. So let me know if you have any questions, and I'll be happy to answer that via email as well. So I'll pause to see if you have any questions. Not seeing any questions. So with that, I conclude today's presentation and hope you have a good rest of your week. Thanks.